HashCat is an open-source tool that allows us to recover plain text passwords from hashes. HashCat supports many hashing algorithms, and it's optimized to use Jew hardware to speed up recovery efforts. I hope you'll join me for this course about HashCat. We'll explore how to install HashCat and ensure that it has other software it requires to run. Then we'll use HashCat at the command line to reverse one or more hashes through a variety of methods, such as dictionary attacks, brute force attacks, and hybrid attacks. And we'll finish up with some practical examples that security auditors or system administrators might face in their daily work. HashCat is useful for testing the security of hashing algorithms and passwords that we use, and it's also helpful to recover passwords for our own files that we may have forgotten. Let's get cracking. What is HashCat? HashCat is a free and open source program that we can use to recover passwords for many different kinds of hashes, and that's useful because the strength of passwords is a cornerstone of digital safety. When we're using HashCat, it's important to recognize what HashCat can do and what it can't. It's great at cracking hashed passwords, but it doesn't decrypt information or derive private keys from public keys. HashCat is a specialized tool that's a critical component of any cybersecurity professional's toolkit, and it's often used in combination with other specialized tools. So before we start cracking hashes, it's important to understand what a hash is. A hash is the result of applying a hashing algorithm to plain text, resulting in output that's a fixed length. When a specific piece of text is run through a given hash algorithm, the result is consistently the same. For different pieces of text, the results will be different, though each input will produce consistent results every time. Passwords are a key component of account security, and in order for a service or tool to allow a user access, that service or tool needs to know when the user has provided the correct password. However, it's a very bad idea to simply store or transmit a user's password, or any kind of password or secret key in plain text. Instead, services often store the hash of a password. In this way, the stored password information is theoretically not recoverable if the hashes are leaked or improperly shared. However, there are ways that we can determine what plain text a hash represents. Often, the hashing process will involve another piece of data called a salt, which is usually derived from or related to the user's account or information in some way. Other times, that salt value is predetermined. In either case, it's added to the hashing process to generate the hash that is ultimately stored on an authenticating server. The purpose of the salt is to make it harder for an attacker to recover the plain text represented by the hash. When the user provides their password to log in or unlock a file, or do whatever they need to do, the password they provide is run through the hash algorithm, and the result is compared to the stored hash. If it matches, access is granted, and if it doesn't match, access is not granted. There are many different algorithms that can be used to compute the hash of plain text. These range from algorithms like MEFDIV and TNOM, which are designed to be fast to calculate, but are rather trivial to recover passwords from these days, to other algorithms like BUACT and CADFOC, which are slower to calculate, and therefore slower to recover passwords from. Those are widely used to protect login information and other information in many operating systems and other tools. These algorithms that are designed to be resistant to attacks are called slow hashes, and sometimes those aren't as efficient to crack using a Jew, but in most cases HashCat can still work with them. HashCat supports many hashing algorithms, and we'll see how to apply the appropriate algorithm to whatever task we're working on later in the course. Hashing algorithms are theoretically one-way operations, meaning that we can't do clever operations with just a hash and recover the original text that it represents. So how does HashCat crack or recover passwords? What HashCat is doing when it's recovering passwords from hashes is just generating hashes with whatever hashing algorithm our target hashes are using, from text strings that we provided or that we tell it to generate. And then it compares the result of hashing each of those candidates with the hashes we're looking to recover passwords from. If a result matches, we've found the password for that hash. HashCat allows us to generate password candidates, and in doing so, hopefully match a hash's password with a variety of attack methods. We can perform a brute force attack, where HashCat generates its own combinations of candidate passwords to test against a hash. This is computationally expensive and time-intensive, so it's only really something we'll want to do when we have absolutely no idea what the password that a hash represents might be. To use this kind of attack, we'll define a mask to tell HashCat to use a specific kind of pattern. If we have a general idea about what a password looks like whether it's 6 characters or 8, or whether it's probably all alphanumeric characters instead of more exotic symbols, or something like that, we can also use a dictionary attack, where we provide a list of candidate passwords, and HashCat uses that to test against the hash or list of hashes. This is significantly faster than a brute force attack, because the key space, the count of possible solutions given a provided set of options, is limited to a known set of values. But it does rely on the password that we're trying to recover being on that list. These lists often contain frequently used passwords, though, so if the password we're trying to recover has been widely used and has been leaked or otherwise made available to one of these lists, we can save a lot of time with a dictionary attack. We can also use a variety of hybrid attacks, where we tell HashCat to combine dictionary and brute force tactics in various ways. This is helpful if we know part of a password, or if we have some sense of how a password might be formatted. And we can use an association attack when we know something about a particular hash, and we can provide that information to HashCat. When using some of these modes, we can also provide a detailed set of rules that HashCat can apply to check variations or permutations of the information we provide, and we can provide sets of characters that HashCat should use in its brute force attempts. We'll explore these attack modes and options in more detail throughout the course. HashCat is optimized for use with GPUs, or graphics processing units, commonly called video cards or graphics cards. These devices compute information in a different way than most of our regular CUS, and the way they work makes them excellent at many of the hashing operations that HashCat performs. In order to communicate with GPU hardware, HashCat can use either vendor-provided software that enables this kind of computation, or it can use OpenCL, a software framework that allows computational operations to be run on a wide range of hardware. While HashCat is optimized for GPUs, we can still use it with a CUE, though the performance using a CUE will often be much lower than it would be with a powerful GPU. We can also configure HashCat to use more than one device for its operations, whether that's a GPU and a CUE, or 2 or more GPUs in 1 or more computers. Because of how GPUs operate, sometimes HashCat won't be able to provide enough work to take advantage of a GPU's full parallel power. We'll still be able to crack hashes, but the effort might be slower. There's a couple of useful entries about this in the HashCat frequently asked questions. I encourage you to browse through the FAQ, the HashCat wiki, and the HashCat forums, all of which contain very useful information on all kinds of aspects of using HashCat. HashCat is a command line tool, and it has a lot of command line options, though only a few are required. So after we install HashCat, we'll spend some time looking at common options, and I'll show you how to look up the details on how to use them. Before we get started working with HashCat, though, I want to share one very important disclaimer. We should only attack hashes that we have permission to work with. Tools like HashCat that are able to recover information that is intended to remain protected can be used to violate trust, and so it's up to us to act in a trustworthy way when practicing using these tools. And depending on where you live or work, tools like HashCat may not be permitted, so be sure to follow your local laws and regulations, and only use HashCat in ways that you have permission to. Another item to note here is that when we're working with word lists, which we would usually download from the internet, we're likely to come across adult language and possibly surprising terms. People choose all kinds of interesting things as their passwords, and passwords get leaked, so these interesting passwords show up in many lists. I'm going to do my best to keep that kind of thing out of the videos here, but you may see words you don't like when you're working with downloaded word lists on your system. What you should know: throughout this course, I'll be using my GPU. I recommend that you also follow along with a Linux system and a reasonably capable GPU, but you can also use Windows or Mac OS and a less powerful GPU or your CUE. We'll see how to do that shortly. Just be aware that the cracking performance for more challenging hashes without a powerful Jew will be much lower. Along with the course, I've provided a variety of hashes and word lists, so we have something to practice with as we learn how to use the HashCat software. These hashes are pretty weak ones, and the passwords they represent are fairly short, much shorter than real passwords ought to be. That's because we're focusing on how to use the software and how to plan a cracking session, and not on spending the hours or days or months it might take to crack real passwords. These hashes were all generated with common Linux command line tools. You can use this password list as a reference for our cracking activity. Throughout the course, we'll recover these passwords from the hashes. I've designed this course around very easy to crack hashes so that you can follow along regardless of the hardware or operating system you're using. As I mentioned, we'll be spending this course learning how to use the basic functions of HashCat and exploring how to plan a cracking session. HashCat has many features, and I encourage you to explore the man page or help documents to find out even more details and spend some time with the HashCat website at hashcat.net and the various guides and wiki entries there. Installing HashCat and required software. We can run HashCat on Linux, Windows, and Mac OS. For each of these operating systems, we can build HashCat from source if we're so inclined. We won't do that here though. Over the next few videos, we'll take a look at installing HashCat on each of these operating systems. I'll be using Linux throughout the course. Before we install HashCat, I want to spend some time talking about software that we'll need in order to run HashCat once it's installed. That software will be determined by the hardware we plan to use. To run HashCat, we can use Jew hardware, CU hardware, or accelerator cards. And to use these devices, we'll need to install various software tools. If we're using a Jew, we'll need to install the appropriate Jew driver on our system, but we won't quite be ready to use it with HashCat yet. We'll also need to install separate software that allows HashCat to use the Jew as a computational device, and there's two primary choices for this. If we're using NVIDIA card, we'll need to install the CUDA toolkit. And if we're using an MJU, we'll need to install the ROCm software on Linux or the HipSDK on Windows. Or we can use OpenCL, a software framework that's designed to run computational tasks on a wide variety of back-end hardware. We'll still need Jew drivers if we use OpenCL though. OpenCL allows us to use a system's Jew or CU for cracking hashes. We can use OpenCL in various forms. For example, Intel provides OpenCL toolkits for use with a CU or a CU and its integrated Jew. And there's free open source projects called POCL that supports a lot of hardware as well. The vendor-provided software will generally perform better, but OpenCL implementations are also available if you choose to use them. OpenCL can also be useful if you have hardware like accelerator cards or devices that don't have specific accelerator frameworks built for them. Modern Jew drivers and these computation toolkits are quite large in terms of the space they'll use when they're installed, and they take a while to install. So when you install the relevant software for your system, be sure to set aside both space and time to do that. I've included a table in the exercise files that describes where you can find installation information for the various options that I've mentioned. If you don't know what kind of CU and Jew hardware you have, you can use various approaches to find out. On Linux, you can use the scup and slopc commands to explore your hardware. On Windows, you can look in your system information area or your device manager. And on a Mac, you can click on About This Mac in the Apple menu and choose More Info to see your hardware details. I recommend that you pause the course here and take a moment to explore what hardware you have and which of the software options you'll need to install. Once you know what combination of software you'll need, you can take a moment to install that, or you can wait to install it after we've installed HashCat. And if you're not sure what you need, don't worry. We'll take a few minutes in the next videos to go through some details for each major operating system. Regardless of how you install though, I recommend cloning the HashCat GitHub repository because it contains all kinds of useful things like rules, character sets, and other tools that we can use during our cracking sessions. Install HashCat on Linux. On a Linux system, installing HashCat is generally pretty straightforward. HashCat is available in the repositories for most distributions, so we can get it installed using our package manager. On Ubuntu, Debian, and other Debian-flavored distributions, we'd use apt install HashCat. And on other distros, we'd use whatever package manager command is appropriate, such as danf install HashCat. We can build the software from source if we're so inclined, or we can download pre-built binaries from the HashCat GitHub repository. I've chosen to install HashCat using my package manager though. Whichever route you take is up to you. To check that HashCat runs after we've installed or downloaded it, I'll run HashCat. You may see a warning here, or you may see some useful output. If you see the warning, don't worry. That just means that we need to install the additional software that I mentioned earlier. But we know that the HashCat software has been installed, even if we may not be able to do anything with it just yet. If you see some information about your hardware, that's fine too. In many cases, installing HashCat from our distro repository will also install Pockle, an open-source implementation of OpenCL. And that's some of the information we'll see with this information display. If your package manager doesn't install Pockle as a dependency, and you plan to use that software, you can install it with apt install Pockle OpenCL ict or whatever's appropriate for your package manager. ict stands for Installable Client Driver. You're welcome to use Pockle if it works for you, but in most cases, vendor-specific software will get you better performance. Often that's closed-source software though. So, if you have requirements to use open-source software, Pockle can help you out. If you plan to use a CU instead of a JU, you can install the Intel OpenCL toolkit if you'd like. On my system, I have NVIDIA Strex 3080 JU, and so I'll need to make sure that the appropriate drivers are installed. How you do that will be different on different distros, so you'll need to do whatever is appropriate on your system for your hardware. On my Ubuntu system, I've installed the drivers with Ubuntu Drivers Auto-Install. I've also installed the Vindia Qt toolkit with apt install Vindia Qt toolkit. And I've also installed the Intel CU runtime for OpenCL applications on my system, following the directions on the site that I have linked in the course notes. For an AMD card, you'd need to install the appropriate drivers and the ROCm software, which you can find by searching online or through one of the links in the course notes. I can see here in my output that I have the Intel OpenCL software available, and I also have the Qt software available to use with HashCat. Great, we're ready to move forward if we're using Linux. Install HashCat on Windows. We can use HashCat on a Windows system in two ways, through SWIL or Windows Subsystem for Linux, or by using it on Windows directly. To use SWIL, you'd need to install SWIL from the Windows Store, and then follow the instructions for installing HashCat on Linux, and you'd want to make sure to install the appropriate software based on what JU you have. I've included a link in the exercise files, where Microsoft provides some guidance for using a JU and SWIL if you choose to take that route. Otherwise, using HashCat on SWIL is just the same as on Linux. To get a version of HashCat we can use directly on Windows, we'll visit the HashCat website and download the recent release from there. Or we can clone the HashCat repository from GitHub and build it from source. In either case, we'll start from the HashCat GitHub repository. So I'll visit the repository, and when I'm here, I'll download the latest release over here on the right. It'll choose to download the 7-zip file here. I'll find that file in my downloads, and I'll extract it. Right now I have a folder in a folder, so I'll move this up to my downloads directory to make it easier to work with, and then I'll make sure I move back into that directory. Here's the prebuilt HashCat binary for Windows. Unlike many programs on Windows, we can't just double-click this file and start using it. HashCat is a command line application, so we'll need to use the command line environment or Windows Terminal to run it. Here on my system, I'll open up Windows Terminal with Start, and then I'll type Terminal. On older versions of Windows, you can do the same with Start and then Run and Cmd. When you unzip the HashCat archive, you can put the resulting directory wherever you'd like. I've kept mine in my Downloads directory, so I'll move to that directory here in my terminal. I'll write cd downloads. Then I'll move into the HashCat directory with cd space, I'll start typing HashCat, and then I'll press Tab, and I'll press Enter. And to run HashCat, I'll type HashCat I see a warning here. Because we haven't yet installed the software, we'll need to allow HashCat to use our Ju. Depending on what hardware you have and what you plan to use, you'll need to make some choices of your own. My Windows system here doesn't have a dedicated Ju, but if it did, I'd need to either install the VindiaQt toolkit or the mTipsDK to enable the system to use a Ju for computation. I'd also need to have my Ju drivers installed. Though hopefully, we'd already have those installed anyway. And if you're using your Ju instead of a Ju, you'll still need to install some software to allow HashCat to use that through OpenKel. Depending on your hardware and your system, you'll need to make sure the appropriate tools are installed. On the system, I'll use HashCat on the queue, and to do that, I'll install the Intel OpenKel toolkit. That's available from the Intel website, and you can find a link to this page in the course notes in the exercise files. I'll download the installer here, and I'll run it. Once I've done that, I'll restart my system. I'll open up my terminal again and move into my HashCat directory, and I'll type HashCat. And now I see that in my case, I have devices available through the OpenKel platform. If you install your Ju's appropriate software, you should see your Ju here as well. Great, we're ready to use this Windows system with HashCat. Install HashCat on Mac OS. To install HashCat on the Mac, we have two options. We can download the source code from GitHub and build it ourselves, or we can install HashCat through the Homebrew package manager. If you don't have Homebrew installed already, you can install it by visiting brew.sh and copying the installation script from the main page. We'd open up a terminal window and paste and run that script. Installing Homebrew involves installing this code command line tools as well. So Homebrew hopefully checks for that, and gives us the opportunity to install it if we don't already have it installed. Once Homebrew is all set up, we can install HashCat with brew install HashCat. Homebrew installs HashCat within the opt Homebrew seller directory. I mentioned earlier that even if we install HashCat directly, it's still useful to clone the repository, because it contains some helpful things that we'll use in the course. So, I'll visit the HashCat repository here on my Mac, and clone that into my Downloads directory. I'll click the green code button, and I'll copy this URL to my clipboard. Then I'll move into my Downloads directory, and then I'll clone the repository with jclone and the URL that I copied. You could put this wherever on your system you'd like. I'll move back to my home directory. On a Mac, HashCat uses the Apple Metal framework to perform calculations with the available hardware. This framework is already available on Macs, so we don't have to install anything separately like we do on Windows and Linux. So if you have a third-party Ju in your Mac, it will need to have the appropriate drivers installed. To check that HashCat has been installed, we can run HashCat, and here we can see not only that the program is working, but also that it's picking up our hardware. In my case, with the Apple Metal framework, and also with Apple OpenKel. Great, we're ready to use this Mac with HashCat. Selecting and testing your hardware. When we're working with HashCat, we'll need to know about our platforms and our devices. In this context, a platform is the software stack we're using to access a device. These devices are the Ju or accelerator hardware. If we have OpenKel or one of its implementations installed, we'll see the OpenKel platforms available to use. Or if we have vendor-specific tools like Kudo or Ream installed, we'll also be able to access the related devices directly. HashCat will automatically select what it thinks is the best device or device and platform combination, and if we have one or more JEPs, that's what HashCat will use. But it's good to take a look and see what all the options are. As we've seen, I can get my HashCat backend information with HashCat. For example, here on my system, I have two OpenKel platforms installed. One is the Intel OpenKel platform, and the other is the VindiaQt OpenKel platform. In my case here, I can see that the Intel OpenKel platform has id1, and my Ju has the backend device id2. The Vindia OpenKel platform has id2, and here my Ju has backend device id3 alias 1. If I scroll up a little bit more here, I can also see my Ju represented up here under the CRUD information, where its backend device it is 1, alias 3. It's the same device but accessed in two different ways. I'd be able to use my Jew through the Vindia OpenCell API if I want to, but I'll be using CUDA directly here on my system. On your system, you're likely to see different information here, so take a moment to explore the output of this command to get an understanding of how your devices and OpenCell platforms are related to each other. If you have NVIDIA or NGU, you're probably going to be better off using the vendor software directly, but if you're using a CU or another device that doesn't have dedicated support, OpenCell should enable you to do that, either through an implementation like POCL or from a specific vendor like Intel. I'll clear my screen, and now let's spend a moment to run a benchmark. A benchmark provides an estimate of the computing capability of the hardware that we're using. To run a benchmark, I'll run HashCat B. This should take a couple of minutes to run. We could interrupt the process with crefc if we want to end it early. Okay, let's explore some of what's going on here. I'll scroll up to the top. Here, we have some information about what devices and platforms are available and being used. In this section here, I can see that I'm using my device number 1 through CUDA. I can tell that because the other devices have skipped after them, but this one wasn't skipped. I can also see that this was the device that was being used. If I scroll down here and look at the number after the speed entry, there's an entry here for each hash type being benchmarked. First is hash mode 0, which is the MEFDIV algorithm by itself. This number here is the hash rate, in my case, about 57.0 MHz or 57.0 mega or million hashes per second. Different algorithms will run at different speeds. This is a fast hash. After this, we can see how long this benchmark took to run and some details about that specific run. This information is relevant to my Jew, and on different hardware, we'd see different numbers here, as we would with the hash rate itself. The benchmark gives us a good general sense of how capable a given device is for this kind of cracking work. As I mentioned, HashCat defaults to using any JEPs that it finds through their own APIs, if available. So in my case, HashCat has selected my Vindia card using QWERTY, and if I had more than one Vindia card, it would use both. Usually, this is what we want to have happen, but I have some other choices as I saw with the backend information from earlier, or which I can see in the output at the top of this benchmark. We can use the D option to tell HashCat which specific backend device or devices to use, and we can use the D option to tell it what type of device to use. HashCat defaults to a Type 2 device, which is a Jew. So if we wanted to use a CU instead, we'd need to use D1. To benchmark my CU, I'll type HashCat B done. I'll give this a moment, and then I'll cancel it with Ctrl+C. I'll scroll up here, and notice in this case, device 2, which is part of platform number 1, is the one that's being used. Both entries of my video card are being skipped, and we can see the difference in performance here. We can also use more than one device type for benchmark and cracking, and we do that with something like this. I'll write HashCat B for benchmark done, 2 to use both the CU and Jew platforms, and done, 2 to specify my CU and Jew devices. Once again, I'll let this run for a moment, and then cancel it with Ctrl+C. Here, I can see a difference in the output. In this case, I have speed 1, speed 2, and a total speed of my Jew and my CU combined, though I can see here that my CU isn't really bringing all that much to the party, but every little bit helps. Throughout the rest of the course, I'll just be using my Jew, letting HashCat choose it by default. That's what HashCat is optimized for after all. Benchmark is a useful way of checking that our installation is working the way that we expect it to. The benchmark hashes are randomly generated, and in benchmark mode, we can see what devices HashCat will select automatically, or as we've seen, we can specify others. Using HashCat. HashCat is a command line program, and so we'll provide the information it needs as command line options and arguments, and we'll see the output of the program as it runs on our terminal. On Linux, we can find documentation for HashCat in the man pages with man HashCat, and we can use HashCat's help on any of the 3 platforms to see a detailed listing of options and other information. Broadly speaking, when we use HashCat, will indicate which algorithm we want to work with. We'll provide a source of hashes we want to crack, and then we'll provide information about our attack strategy. There are other options too, but we'll start with these because they're all required. The hash type or mode is specified by the M or this hash type option, and this takes a number as an argument. HashCat supports a huge number of hash types, and there's a list of them in the help and also online. For example, 0 is Maevdiv, 100 is Shan, and so on. We'll explore these and others in a little bit. HashCat can try to automatically determine what kind of hash we're using, but it's usually best to be specific and tell HashCat which mode to use. The next item that's required is a file that contains one or more hashes that we want to reverse. We'll have just one if we're targeting one file or a login, for example, but we'll also often see HashCat used with a long list of hashes that might be from a source, like a user database or something like that. We'll see how to find this information in a later video. The last required information when we're using HashCat is the information about what attack strategy to use. We'll specify this with a or attack mode. As with the algorithm section, we'll use a number here, and the numbers for the modes are listed in the help documentation. 0 is a straight attack or a dictionary or word list attack. 1 is a combination attack. 3 is a mask attack. Mode 6 and 7 are hybrid attacks, and attack mode 9 is an association attack. When we type our HashCat command, it's fairly conventional to leave a space between the option and the value, but that's not necessary. Though, the order of the items does matter to a degree. For example, here we might use hash mode 0, which is Maevdiv hashes, on a list of hashes called hashes TSDS. We might choose to use a hybrid attack mode, in this case, 6, which combines strings from a word list with a sequence of characters that HashCat generates. In this example here, that would be a 3-character long string made up of common characters. We'll explore this all in more detail later on. We'll also often want to use the O option, which tells HashCat to use an optimized kernel. A kernel is the specific implementation of code that HashCat will use for a given hash. Some of the hashes have optimized kernels available, which work faster or more efficiently for that particular hash. Optimized kernels also often limit the length of passwords we can recover, though in many cases that limit is fairly generous. If there's no optimized kernel available, HashCat will fall back to the pure kernel for that job automatically. And we'll usually want to provide a file for the recovered hashes to be stored in for easy reference. When HashCat runs, it outputs information to the screen. Most of this information is about the progress of the cracking activity, how long it's been running, what the estimated time of completion is, and so on. It does an update for every result. That would be a bit chaotic because HashCat is often running through millions or billions of candidates, so by default, we get an introductory status update, and then we can press S to see the current status whenever we'd like to. This output shows a large amount of information, and we won't go through each line here, so I encourage you to spend some time looking at the output when you run your cracks. Generally, though, we'll see the session name, the current status, information about the hash mode, and the starting time and estimated finishing time. There's also other information about how the process is running, like its speed, how many hashes are recovered, how many candidates were rejected, and so on. Here we can also pause, resume, or quit the operation. Pausing keeps HashCat running, but stops the evaluation efforts, so it's something we might do if we need to give our compute resources to something else temporarily. If we quit the operation, HashCat saves its state but will specifically need to recall it later, as we'll see. HashCat stores passwords it recovers and their hashes in a file, called a pot file, but that file is mostly for HashCat's internal use, so it doesn't waste resources cracking hashes it's already cracked. While we can read this file and get cracked passwords from it, it's not really for us, so if we want to record our recovered passwords, we'll want to pass along the O option in a file name, where we'll store hashes and their recovered passwords. Depending on our platform and how we installed HashCat, the pot file will be located in different places. Here's a list of some common locations. There are other options too. As I mentioned, and we'll see some of these in later sections. We can use these options to change how HashCat behaves with resources, and we can save and restore sessions. We can change devices and specify what ranges of files to work within, and so on. Remember to refer to the man page or help information to see what options are available and how to use them. Because HashCat is command line software, and it often takes a while to run, it's a good idea to use a terminal multiplexer, like TumpCS or Screen, so your session won't be interrupted by a broken connection or accidental closure of a terminal window. It's always best to let HashCat close or quit on its own terms, where it can write its progress in the expected way instead of just being terminated unexpectedly. As I mentioned, we'll see how to set up sessions in order to save and resume our work, but Screen and TumpCS allow us to use the same terminal window for different tasks in case we choose to switch away from a HashCat session and do something else while that's running. To learn more about TumpCS and Screen, take a look at my course, Linux Multitasking at the Command Line, and if you're not comfortable working at the command line, check out Learning Linux Command Line to become more familiar with it. If you're following along using Windows, and you're not familiar with the modern Windows terminal, take a look at Windows terminal skills here on our channel. Getting and identifying hashes. In order to crack a hash, we must first get a hash somehow. This will primarily happen in one of three ways. We might generate a hash ourselves using tools like Meetverschmis or SHA-256, or OpenSil, or Tapassword, or some other tool, starting with a password that we know in order to practice our skills and test out our hardware. That's what I've done to create the hash files we'll use as we explore how to use HashCat in this course. Earlier I mentioned that we can generate our own hashes with a shell script, and I shared an example of how we do that in the course notes in the exercise files. We can use methods like this to generate one hash at a time, or read through a list of strings to generate many hashes at once, and various products and programming languages can be used to generate hashes specific to those products as well, though you'd need to explore how to get the hash values out if you use those approaches. We might also acquire a list of hashes from some source, like a system that we've set up, which stores hash passwords, or from a file where hashes are stored in text like the shadow file or various other security-related files on a Linux system. In these cases, we need to copy and paste the hash from that source into our file that we'll be working with. In either case, whether we generate hashes or acquire them from somewhere else, we'd need to do a little bit of work to make sure the file we're working with that contains the hash or hashes is formatted so that there's one hash per line and nothing extra in the file. Some types of hashes will have a username associated with them, and we can tell HashCat to ignore these with a --username option. But otherwise HashCat is fairly picky about the format of the hash list that it reads, so a little bit of preparation work is usually required, and we'll see how to do that shortly. Sometimes we'll need to recover passwords from password-protected files, and in order to do that we'd need to extract the hash from the file so we can work on it with HashCat. There are a variety of tools to do this. Usually one dedicated script for each kind of file that we want to work with. HashCat includes a few of these in the tools directory if you've cloned the repository. There is also a very useful set of hash extracting tools provided with the software, John the Ripper, which is another password recovery tool, which is good to learn about. John is more optimized for working on the queue, and it excels at certain types of hash. To download the hash recovering tools from John the Ripper, we'll visit the repository for that tool and either download the zip file or clone the repo, depending on how we want to work. I'll click the green code button and copy the URL to clone the repository. Then on my system I'll write git clone and I'll paste that URL. The useful tools for extracting hashes are in the run directory, and they're scripts in a variety of languages, mostly Perl and Python, each designed for a specific kind of file. For example, here's fdef1, a Perl script, and there's also a Python version. These will read a def file and output the hash of the password if there's a password on the file. I've mentioned that these scripts are written in a variety of languages, but they're all executable, so we can run them as we would any other executable program, so long as we have the appropriate interpreter installed. I'll move back to my home directory, and clear the screen. Let's run the Perl version of def1. To do that, I'll write /john, run def1.play, and this file expects an argument, so I'll provide the path to a def file. In this case, one of the challenges from the exercise files. I'll run this, and the output that I see here includes the file name and the hash information. We only need this part of the information here, the hash itself, so we could copy and paste that, or we might run this program and redirect the output to a file, and then go in and modify that file to remove the part that we don't need. In fact, let's do that. I'll rerun my command and I'll redirect the output to def hash. The name of this file doesn't matter, but this describes what's in it, so I'll use that for now. If you have lots of files you need a hash from, you might write a shell script or something like that to process the files and put their hashes each on their own line in a text file. I just have one hash here, so I'll open up the file and I'll remove the part up to and including the first colon. Depending on your workflow, you might want to keep a copy of the file with the name and the hash so you can line up which hash belongs to which file later on. But HashCat doesn't need this first part, so we'll remove it here. I know I'm only working with one def file, so it doesn't matter if I keep the file name around. Okay, I'll save that, and now I have a hash to use with HashCat. We know this hash came from a div file, and the hash even says def at the beginning of the string, but we'll need to know precisely what kind of hash we're using in order to tell HashCat which algorithm to use. And remember, that's a number. There's a list of example hashes for each type that HashCat knows about on the HashCat site, and we can use that resource to compare what we have. This is interesting to browse, and it's also a good source for hashes that we can test out ourselves. Here we can see that some hashes reflect just a hash of a password string, and others expect the password and sometimes a salt added to it in various ways. Some hash types represent multiple iterations of hashing, and some with links we can click on to download the data, are binary instead of text. Some hashes are vendor-specific, and others are widely used in various applications. While we can glance at some of these hashes and see which one matches what we have, not all the hashes we might work with are visually distinct from each other, so it's useful to use a tool to tell us what kind of hash something is instead. If we don't know what kind of hash we have, we can use HashCat to give us the information that we need. If you have a Linux system, you can install HashCat from your package manager like apt install HashCat or similar. If you're on another system, you could install it with pip, the Python package manager, like pip install HashCat. In that case, it's a good idea to work within a virtual environment to keep your tools separate from the system tools. Here on my Linux system, I'll install HashCat with my package manager. I'll write apt install HashCat. Okay, I'll clear the screen. Now, we can use HashCat with the -m option, which will tell us the appropriate HashCat mode for a given hash. I'll provide the name of the file that contains my hash, and here, I can see that this hash is def14-16, and we can use HashCat mode 10500 to evaluate this hash. Great. We'll come back to this example at the end of the course once we've learned how to use HashCat. If you aren't able to install or use HashCat, you can compare a hash to those listed on the example hashes page. Sometimes you'll be able to tell visually what type a hash is, but other times it's hard to tell just by looking, so you may need to try out a few different modes to see if you guessed correctly. Using HashCat is much easier though, so if you're able to use it, I recommend that. And remember, HashCat can try to identify the hash type from the hash list, but it's usually better to be explicit. Whether we're working with many hashes or just one hash wherever they're from, we need to do a little bit of homework to get the hashes in the proper format in files we can give HashCat. And we'll need to figure out which specific mode to use. But once we have that work done, we're ready to use HashCat to recover passwords. In the next few videos, we'll spend some time working with the various attack modes to learn more about how they operate. I'll be using the mefdiv hashes file I've provided in the exercise files. Mefdiv is a hashing algorithm that's been around for a long time. It's often used to produce a hash as a signature for a file or a long string of text, which can be used to verify that the contents of that file or string are almost certainly the same as what the hash was derived from. We'll often see this method used to verify software downloads and things like that. mefdiv is also unfortunately sometimes used to hash passwords. I say unfortunately because while the mefdiv algorithm does take some computation, modern JUPs can run an unimaginable number of mefdiv hashes per second, and yet now and then, we'll hear about leaks of user databases with passwords only represented by mefdiv hashes. Yikes, I'm going to be using mefdiv for many examples here, because they're fairly easy to represent and understand, and most hardware should be able to crack the examples we'll use in a relatively short time. Have also provided some other hashes that have the same passwords in a couple of other formats, if you want to explore using those on your own. After we've learned how to use the basic features of HashCat, we'll move on to some more practical examples using more realistic hash types, including this def file. Dictionary attacks. The first attack mode we'll explore is mode 0, or what's called a straight attack or dictionary attack, or a word list attack. This mode works with a text file, called a dictionary or word list, that contains entries that HashCat will try as password candidates. Often when we're performing this kind of attack, we'll rely on a very long list of passwords that have been leaked or otherwise made available through various means. This attack is the fastest attack mode, generally speaking, because it has a rather limited set of options, making for a relatively small key space the count of the individual candidate passwords that our attack is going to try. The downside of this kind of attack by itself is that if the password isn't on our list, HashCat is not going to find it. We'll see how to make this mode a little bit more flexible later on. A dictionary attack is useful if we suspect that a password is one that is commonly used, like 1234 or summer 2023 or passworth as spelled with a 0 instead of an O or something like that. Unfortunately though, basically all of these simple or common passwords have been leaked at some point, so they appear on various word lists. One of the large popular word lists is called RockU, and you can find that list online should you be interested in using it. There are many places to get word lists, and there's a great collection called seclists on GitHub here. Many of these word lists are quite long, so we'll just practice with some short lists in this course. But the mechanics are the same if you choose to use these longer or more specialized lists. Just be aware that it's common for them to be tens of thousands of lines long or more. We can tell HashCat to use a directory full of word lists instead of just a single file, if we have a lot of word lists. I'll switch back to my terminal here and I'll move into my exercise files. In my very basic individual word list here, I have 40 options, and I have 50 hashes in my mefdiv hashes file. So using these files, let's run our first attack. I'll write HashCat for modin 0. That's mefdiv. And then I'll provide the file that has my hashes in it, in this case, mefdiv hashes. Then I'll write a 0. Attack mode 0 is the dictionary attack, and the dictionary or a word list that I'll be using here is basic list. Then I'll use O to request an optimized kernel, and we'll use O, and then I'll provide a file name to collect the results, in this case, results.tsts. I'll run this and we can see what's going on. What's going on here is something that we could really do by hand if we wanted to, hashing each word in the list, and then seeing if it matches the hash we already have. We could do that with some common tools and a short batch script, but this is a very small example, just to explore how to work with HashCat. Okay, it looks like I have some results here. I can see in this line here that HashCat recovered 5 out of the 50 hashes. Great, let's take a look at those with cat results, tsts. Okay, here we see the hash that was cracked, a colon, and the password that was recovered for that hash. If we looked at our basic word list, we'd find each of these words there. Let's try to crack some more hashes using a different word list. I'll clear the screen. Once again, I'll type HashCat and I'll use my same hash list. I'll use the same attack mode, but this time I'll use second list. I'll use O and I'll put these results to results tsts as well. And there we go. We already have 10 of our hashes cracked just using these basic word lists. Let's take a look at those. Okay, but it seems that the rest of the hashes are going to need a different strategy. We can also apply rules to a dictionary. Rules allow us to tell HashCat to transform words in some way, like replacing a certain character with another one or trying out uppercase versions of certain characters and so on. We'll see how to do that in a later section. Combinator attacks. Another mode that's related to the straight or dictionary attack is called a combinator attack, and it allows us to use two word lists, and HashCat combines each entry from the first list with each entry from the second list as candidate passwords. This mode has the number 1. For example, if our first list had apple, melon, and banana, and the second list had red, green, and yellow, if I used mode 1 and list only and then list wa, HashCat would generate all of these combinations as candidate passwords, hash them, and compare them with a list of hashes. With a combinator attack, we have a list that's considered to be the left list and one that's considered to be the right list, and this affects how the lists are combined. If we swap the order of those lists, in this case, we can see how the results would change. Let's use the two lists that I have here in our hashes file to see how this works. We haven't cracked all the passwords in the hash list yet, so let's see if a combinator attack will help. I'll write HashCat M0 because we're using mefdiv, and provide my list of hashes. Then I'll use dash, lowercase a and 1 for the combinator attack. This takes two arguments, so I'll provide my basic list and my second list, and once again, I'll use an optimized kernel, and I'll send the results to a file with the results.txt. I'll run this, and it looks like I've recovered 5 more passwords. Great. Below that, I can see that my progress when I'm done is 1600 out of 1600. HashCat has tried 1600 combinations of words, and we can see some of those here. For example, we can see the word blanket combined with the word plant, and the word window combined with the word silver. So let's see what passwords we found. I'll write cat results.txt, and here's my 5 most recent additions. While each of these words like blanket or guitar desk or bridge appear in the lists, the combined words blanket, guitar desk, bridge, and so on don't appear in any of the lists. HashCat has generated them for us. It can be interesting to see the full set of combinations that are generated from lists, and we can do that by adding the styd_tout option and then taking out the hash list. Then HashCat will show us the list. Let's take a look at that. I'll clear my screen and I'll write HashCat 1 basic, list second list styd_tout. I could output this to the screen or send it to a file with the O option. I'll just send it to my screen here, and I can see all of the combinations that HashCat has generated from these two lists in this order. Earlier I mentioned that the order of the lists matters, so let's switch the order of our lists here and see if we can recover any more passwords. I'll clear my screen and I'll rewrite my command again. I'll write HashCat M0 bft of hashes a1, and this time I'll put the second list first and my basic list second, and again, I'll put the results in the results file. I'll run this, and I can see now I have 20 passwords recovered, so it looks like this version of the attack found 5 more. We'll take a look at the results. And here, under the previous 5, I have 5 more. Good. We're making progress. Dictionary attacks are useful for quickly finding hashes for passwords that are within a known set, or which are commonly used passwords. We might use a straight dictionary attack to ensure that passwords in a system that we're auditing are not those which appear on lists of leaked passwords. This kind of attack is not so much about evaluating the strength of a password, but rather evaluating whether or not it's one that's known to be compromised, and a combinator attack gives us a different strategy for using two words lists together in various ways. Later, we'll see how we can begin to transform words on the list to look for slight variations. But if the password for a hash we have doesn't appear on the list, or if it's actually sort of unique, how do we crack that? Well, in that case, we might need to turn to brute force. Mask attacks. If we are unable to find a password for a given hash on a word list, we need to take more extreme measures. A brute force attack generates all combinations of characters and tries them against the hash. This is, to a reasonable extent, basically guaranteed to discover the password for any hash we might have. The problem, though, is that it takes forever. At least it takes forever if we don't provide any boundaries and we just tell HashCat to generate every possible combination of every character it can represent. This is called a naive attack. As you might imagine, in the case of recovering passwords, a naive brute force attack is not very efficient. Most of the time, passwords are made up of easily typable characters, not exotic characters that we need to use special modes or something like that to type in. So to make a brute force attack quite a bit more efficient than it otherwise would be, and to avoid wasting time generating unlikely combinations, we can provide HashCat a mask to limit the scope of the generated keys. A mask attack allows us to tell HashCat how many characters we think the password is and what set of characters to try, and then HashCat generates all the combinations that fit within the constraints we provide and tries each of them against the given hash. A brute force attack is mode 3. We represent a mask using a series of tokens, which each represent a specific kind of character. These tokens start with a question mark and have a letter representing their associated character set or char set. So for example, we can specify a lowercase or uppercase letter, a digit or a symbol, and this set of symbols includes the space character. We can also use uppercase or lowercase hexadecimal values or hexadecimal byte values. This can be useful if we're recovering passwords that use other text encodings, as we'll see shortly. There's also a special token, which includes the lowercase and uppercase letters, digits, and symbols. We can also define custom character sets, which we'll explore later in the course. For now, we'll use the built-in ones. Each token represents one character of a password. So if, for example, we knew that our password was 6 characters long and that it was only going to contain numbers, we'd use d6 times, and we could see some of the possible values that mask would generate here. Or we could have a mask that's, let's say, 5 characters, including letters, numbers, and symbols. And for that, we'd use a 5 times, and again, here's just a few examples of what this mask might generate. With so many characters and positions, HashCat still generates a huge number of possibilities, but it's a much smaller solution space than if we allowed HashCat to use any character it could generate, like one of these for example. That's not to say passwords never use these characters, but it's generally less common in a broad sense. In my case here, in this course, I know that the passwords that I'm working with mostly have characters that are in the basic range. Often, password restrictions limit the characters that users can use in their passwords, and this constrains the key space of a password, which is good for us when we're cracking passwords. But as I mentioned, we'll see how to tell HashCat to use other characters by providing a custom character set later in the course. When we make a mask, we can also include explicit text if we know that the password contains a specific string somewhere, like apple followed by any 2 numbers, or with an uppercase letter in front of it, and so on. If we don't provide a mask when we're using a mask attack, HashCat will use a default mask to keep its search space reasonable. Let's write a command to run a basic mask attack. I'll write HashCat M0 and I'll keep using my method of hashes list. Then I'll use a 3 for attack mode 3, and then I'll provide a mask. This will look for a 6-character password using the characters in the asset. That's the lowercase and uppercase letters, digits, and symbols. As usual, I'll use O for an optimized kernel, and I'll output my results to results.tsgs. This tells HashCat to generate an iterator through all possibilities of 6-character long strings using the symbols that are specified. So let's see what we get. This is taking a moment, so I can press S to see the status. Here I can see that it's 27 done, and I can see some of the candidates that it's trying. Okay, we've exhausted that key space. Here I can see how many combinations were tried, and it looks like we have 21 recovered passwords now. That's 1 more than before, so it looks like we got 1. Let's check that out. Alright, cat results tsgs. Here we go. Even though this password looks fairly secure, we were able to recover it in not that much time. I'll clear the screen, and I'll press up a few times to recall my previous command. One of the side effects of specifying a 6-character mask is that this will only find 6-character passwords. If our password is less than, in this case, 6 characters, we won't find that password because we're only generating 6-character long strings. To be more flexible about the length, we can use this increment option, which starts at all 1-character solutions for the mask, then all 2-character ones, and so on up to the full length of our mask. So, this allows us to discover 1, 2, 3, 4, 5, and 6-character passwords. We can shorten this option to just I if we know that our password isn't very short, like 1 or 2 characters. We can start iterating with a longer string with the increment min option. So having recalled my previous command, I'll write increment, and I'll write increment min 4. This will generate 4, 5, and 6-character long strings. I can watch the progress as we go. I can see that it's finished the 4-character space and now it's working on the 5-character space, and now we're onto the 6-character space. Okay, we're done. And now I have 30 hashes recovered. It looks like we got 9 more. Let's take a look at those. And now we have the 4 and 5-character passwords for some of the hashes. Good, we're making progress. Brute force attacks are useful because they will eventually find a password as long as we're using the correct character set. But they take a very long time to run because of the enormous set of possibilities that HashCat has to consider. JUPs are really good at this kind of task, but there's a lot of work to do, so for passwords longer than maybe 8 or 10 characters, even with fast hashes like mefdiv, you'll be waiting for a while, and brute forcing more resource-intensive algorithms can take literally hundreds of years or more. If we know something about the format of the password, we can cut down the solution space, but brute force matching remains something that probably shouldn't be our first strategy in every case. Hybrid attacks. HashCat supports 2 hybrid attack modes which are quite similar. Hybrid modes include a dictionary or a word list component and a brute force component. We can supply a word list and a mask, or a mask and a word list, depending on what information we know about a possible password. A word list and a mask, which is mode 6, would try combinations starting with the words from our list and ending with the generated characters in a mask, which can be useful if we know our password follows this pattern. And the other mode, mode 7, reverses these 2 pieces of information and tries combinations of strings generated by a mask in front of words from a word list. Other than the order of terms, these attacks work the same, but we need to be consistent about how we provide data to HashCat depending on the mode we use. For mode 6, we need to provide a word list and then a mask. And for mode 7, we need to provide a mask and then a word list. Let's explore these modes a little bit again with our fairly basic examples. I happen to know that some of the hashes in our list use a word from our word list and then have 4 digits following that. So let's use mode 6 to crack those. Alright, HashCat M0 mefdiv, hashes and 6 for attack mode 6. This is the one that takes a word list and then a mask, so I'll provide my list and then I'll provide my mask, which, as I mentioned, is 4 digits. So that's I'll use O, and I'll put my results in results TSDS. I'll run this and I can see how HashCat is generating these candidates. In this case, there were 400 of those, and now we have 35 recovered passwords. So let's see what we got. I'll write cat results TSDS. Here I can see the most recent 5, Lampite 1000, 819, Pencil C 1271, and so on. For the next set of hashes in our list, I again happen to know that they have a lowercase letter, 2 digits, a symbol, and then a dictionary word. So let's use attack mode 7 for that. I'll clear the screen and I'll write HashCat M0, provide my hash list, and this time we'll use attack mode 7. The mask I'll use is Dales. And in this case, let's use our second list, and we'll put the results in results TSDS. We're up to 40 recovered passwords. That's 80 of our list. And on this run, I've recovered 5 more passwords. Let's take a look at our results again with cat results TSDS, and here, we can see those, for example, 41 bucket, a 37 tiger, and so on. Good, things are moving along. In these cases, because we knew something about the format of a password, namely that it was either a string that appeared in a dictionary and 4 digits after that, or that it was a lowercase letter, 2 numbers, and a special character in front of a word from the dictionary. We can massively reduce the key space that we otherwise would have had to use in a fully brute force attack for the full length of each password. And we've added some variability from just a straight attack or a combinator attack. So we can think of hybrid attacks as a kind of more flexible combinator attack, where one side or the other of the combination can be generated rather than being static input. Hybrid attacks can save time as compared to fully brute force attacks, as long as we know some information about the password, and that knowledge of the password allows us to build a strategy that works with hybrid attack modes. Association attacks. There's another mode we can use with HashCat as well, and that's called an association attack. It has attack mode 9. It can be used if we have salted hashes, and we know something about each hash's corresponding salt, and we want to use that piece of information in our attack. This kind of information is usually either a username or a known salt that we know applies to a given hash. The attack is called an association attack because this hint or piece of information is associated with one hash, and in this mode, HashCat only uses that information instead of trying other known salts. So it's not a mode that's useful for the situation where a list of hashes likely share the same one or few salts. We'll supply what we think we know about the salt as we would supply a word list, with each one hint lining up with each one hash in the hash file. These files need to be exactly the same number of lines and have a one-to-one correlation between a hash and a hint. We can apply rules to this attack like we can with basic dictionary attacks, and we'll need to output the results to a file. Because there is only one hash being solved per hint, HashCat doesn't save the recovered hashes in the pot file because in this circumstance, there are likely no reuses of the same hash and salt in a given hash file. Ordinarily, when HashCat recovers a salt for a particular hash, it'll use that salt in attacks on other hashes in the list. That's resource intensive, and this association attack mode is designed for the case when we know that salts aren't going to be reused in a given hash list. If you need to recover passwords that you know are the result of a salt being calculated on a per user or per hash basis in some predictable way, this is likely a good attack to run, but in most cases, other attacks are likely a better strategy. You can read more about how this mode works on the HashCat wiki, and learn more in the maintainer's post about it on the HashCat forum, which is linked at the bottom of the wiki page. Now we've seen the primary attack modes that we can use with HashCat. As we'll explore more when we plan our attack strategy, we might use more than one mode in sequence for a given task. For example, we might run a simple dictionary attack against a large hash list just to quickly see if any matches are found, and then we might choose a different strategy for the remaining hashes. In order to best utilize our resources and our time, we'll also apply other strategies like rules and things like that as appropriate. We'll take a look at that next. Transform word lists with rules. Rules are sets of operations that we can apply to a word list, which transform each entry in a specific way. This means that we can use rules in word list attacks like mode 0, 6, 7, and 9. Rules definitions are a whole programming language unto themselves, so I want to just introduce you to them here. Rules are written using a rule syntax that describes how to transform each item in a list. There's a reference for the rules operators here on the HashCat wiki. And we can see that it's not exactly something that we'll be able to memorize on the first try, but the rule syntax is powerful, and it lets us mutate our attacks in ways that capture realistic scenarios. So this page is worth bookmarking for future reference, both if you're writing rules and if you need to read them. HashCat comes with some rule sets that cover common use cases, many of which result from observed patterns, and strategies that inform what we see in leaks of passwords over time. These include rules that toggle the case of letters in various ways, shift or double letters, or turn regular words into leet-speak by replacing the letter A with 0, A with 4, and so on. Let's make sure we've cloned the HashCat repository, and then we'll spend some time exploring the rules it provides. I'll visit the repository and copy the URL. And then here on my Linux system, I'll move back to my home directory and clone that repository. Then I'll move into HashCat rules, and let's take a look around. Here's quite a few rules. Let's take a look at two in particular here, we'll look at best66 and Unix Ninja LeetSpeak. To take a look at the top of a file, I'll write headin for a number of lines, and we'll take a look at the first 20 lines of the best66 rule file. This first rule here, the colon does nothing, so this would pass through the exact string in each line in our dictionary, resulting in the same behavior as a regular dictionary attack without any rules. This next rule here, lowercase r, reverses the string from the word list, turning it backwards. The rule U here will uppercase the whole string from the word list. And taro will toggle the case of the character at position 0. So if the first character is an uppercase letter, it'll become lowercase and vice versa. Down here, we'll add numbers to the end of each string. 0 through $9. Sign is the regular expression symbol for the end of the line. And here too. This says at the end of the line, add 0, then 1, then 2, and so on. And if we look a little further down, the next set of rules adds 2 numbers to the end of a string, 0, 0, 0, 1, 0, 2, and so on. We'll see similar behavior with the caret symbol to add things to the beginning of a line instead of the end. It's interesting to scroll through these rules files and consult the documentation to explore what they do. Let's take a look at Unix Ninja's LeetSpeak file. Again, I'll write headfnutme and provide the name of that file. Here we can see a lot of substitution going on. That's the rule S. So for example, this first line here says, substitute the letter A with a number 4. The next rule says substitute the letter A with 4 and substitute the letter B with a number 6. Okay, I'll clear my screen and let's use our hash list again and then do a regular dictionary attack with our basic list. But this time we'll apply the best66 rule to see if any of our passwords for the hash list are modifications of that basic word list that this rule can generate. I'll move back to my exercise files and I'll write HashCat M0 if hash is a 0 for attack mode 0. And for that we'll use the basic word list. We've done this before, but this time I'll add r and I'll provide a rules file, in this case from hashdig in my user directory rules best66. And as always, we'll use the optimized kernel and output our results to results.tsts. It looks like we found a few more passwords. Great, let's see what we got, okay? I can see that these passwords have been modified from what I know is in my word lists. Let's try the other set of rules. I'll include the screen. I'll recall my previous command and I'll change it, best66 rule to Unix Ninja's LeetSpeak rule. Using this rule, we've recovered 4 more hashes. Let's check those out, and here I can see that that rule has replaced various characters with other symbols. I can see how it transformed the word keyboard, picture, blanket, and computer. As with the attacks that we've seen before, we could have arrived at these results with a brute force or mask attack as well. But using a rule set that applies to a dictionary narrows the key space significantly compared to a brute force attack, especially if we don't know where symbols or numbers or other kinds of characters are in the string. When we're using rules, it's useful to keep in mind that they often reflect common patterns that real people seem to have used to generate passwords that end up in leaks. Rule files are really useful, but they're not magical, and like a word list file by itself, if a particular mutation doesn't appear in a rules list, HashCat won't find it. So while we can generate our own rule sets, if we know something specific about the generation strategy for the passwords we're trying to recover, it's also usually helpful to apply rule sets built by others if we're trying to discover passwords we know nothing about. We can apply more than one rule set to a given word list by using the -r option, and a rule set more than once. Or we can use a wildcard to use all the rule files in a given directory. However, if we use more than 2, HashCat will go through and combine them 2 at a time in no particular order. I happen to know that there's one more password that we can find if we use our other list, and a different rule. So let's take a look at that. I'll write HashCat M0 of hashes, a 0 for attack mode 0. And this time we'll use second list. I'll use the rule top 10 2023. And I'll put my results to results.tsts. I'll run this and there we go. Let's see what that password is. I'll write cat results.tsts, and that password was loptopony123. I encourage you to spend some time reading through rules files to look up what they do. Rules are an extremely powerful tool when we're using wordless-based attacks. Using custom charstus. Another way we can customize our attacks is to provide a specific set of characters to use in a mask attack. As we saw earlier, HashCat has a default character set represented by the token L, UDS, the letters A through Z in lowercase and uppercase, the decimal numbers 0 through 9, and a set of symbols. We can also use tokens that represent lowercase and uppercase hex symbols from 0 through F and the bytes from 0 to F. But it may be the case that we need to work with passwords that use specific sets of characters. We can have up to 4 custom character sets per session, but character set files can contain many character sets as long as they're all in the same encoding. We'll refer to each of the custom character sets with a 1, 2, 3, or 4, as we would refer to each of the sets of the default characters in a mask or rule. These character sets can contain the tokens we saw before for the standard characters, so we can use those to build custom character sets, should we need to. This is commonly done when composing a character set where we want to have regular characters and also something special. For example, if we know that our hash comes from an environment where people use a specific language, or more precisely a specific character set, we can use that instead of or in addition to the default English or Roman or ASCII character set. We can pass along one or more individual characters to use, or we can pass along files containing these sets of characters. We'd often set the first character set to lids or the lowercase and uppercase letters, digits, and symbols, and then set the second character set to another set of characters or to a file with special characters, and then we'd compose character set 3 to use both 1 and 2, and then we'd use 3 as a token anywhere we want a regular or special character. Using a character set file is really helpful when we suspect that the password for a hash includes characters that are not in our regular text encoding, making it difficult for us to type the precise special character we might be looking for. HashCat comes with a number of character set files with standard and special characters in various languages and in various encodings that we can use in this case. In order for HashCat to crack a password with one of these special characters, the hash string needs to be in the proper and corresponding encoding though. So while we might be working in Etmanite in our terminal, if we needed to crack a hash with a password in, let's say German encoded using ISO 1859, we can use the corresponding characters at file that contains the characters in that encoding to match the special characters that are outside of the regular HashCat range. Another option is to use the characters explicitly as long as we know they're in the same encoding as our target hashes. One issue with many special characters is that they can be represented by different bytes, even though they look the same to us. In one encoding, a special character might have a certain byte representation, and in another it could be different, and that same byte representation might represent another character instead. And when we're working in Etmanite, many special characters can actually be represented by 2 bytes instead of just 1. In that case, we need to make sure that our mask provides enough space for HashCat to resolve both bytes. If we know what character code we're looking for specifically, we can also provide hexadecimal values for those characters in a custom string along with the charstus option, or as I mentioned before, we can use the byte mask characters, but there's 255 of those, and that adds a lot of complexity if we want to just iterate through them all. 2 of the hashes in the list I've provided are of strings that have characters that I know appear in the German ISO 1859 special characters list. An O with an umlaut and a U with an umlaut. So to find these passwords, we could either use a character set like this, or we could use those explicit hex values like this. Here, the values skix and face represent O umlaut and U umlaut respectively in the ISO 1859 encoding. For other characters, you'd need to look up their hex equivalents in the appropriate encoding. To keep the cracking short here, we'll use a mask that significantly reduces the amount of work, which I can do because I know what the strings are and what pattern they follow. So I'll write my command. I'll write HashCat M0 mfdv hashes and we'll use attack mode 3, the mask attack. I'll set my first custom character set, number 1 to the token. My second custom character set, it'll be one of the character sets in the hashtag directory, so I'll set that to HashCat Charst as standard German D is a 8815 and -1 checks, and then for my third custom character set, a compose number 1 and number 2 together. Then my mask will be question mark for any character, and in the second position, I'll use any character from my custom character sets. Then the next 4 characters will be lowercase letters, and the last will be a digit, and we'll output the results to results.ts. Here I can see that I've recovered 2 more passwords. That's promising, so let's take a look at those. I'll write cat results, CSCS, and well, that's almost useful. But these results are in hexadecimal, so to read the text, we need to convert that to something readable. We can do this with various tools, depending on what's available to us. There's a lot of converters online that can do this hex-to-text conversion, but obviously don't paste sensitive information into them. We can convert this into something readable on Linux with a tool called Skankt, which lets us view files in hexadecimal, and it can convert hex back to text. So I'll echo that and pipe the result into Skankt, which I mentioned earlier, with a couple of options to convert from hexadecimal into bytes, and then I'll pipe that into Icon, which is a tool that can convert from different encodings. I'll use the F option to say that what we're piping into it is coming from the encoding ISO 1815 and I1, which is the encoding that we were using for the password. So we need to use it again to see our special character. I'll run this and there we go. I'll make some more space on the screen here. As we can see here, this password was Sakatufta with an umlaut over the O. Let's take a look at the other one. I'll recall my previous command and replace the text in the echo command. I'll run this and again, I'll make some space, and here I can see that this password was Puzzle Terry with an umlaut over the U. Dealing with encoding gets really tricky, but HashCat does allow us to use special characters in our cracking attempts. Often it's just useful to use the relevant provided character sets sprinkled into your mask when you need those characters. But we can define our own character sets too, and we can use hex values if we really suspect that something special is going on. And keep in mind that we can create our own character set files too, to store explicit characters or masks that we might want to use that are more complex than what fits on the command line. Managing sessions and workload. Password cracking can take a long time, and HashCat gives us a few options to help make the experience of running a long cracking session a bit easier. One useful feature is that we can provide a name for our cracking session, and then if we cancel it, we can come back and restore that session later. HashCat stores information about that session. Things like the command that was used to start the session, so the hash mode, the files, and so on. And it remembers where in the process it was when the session was ended. That saves time when we come back to it, because the process won't need to start from the beginning. And it's always good to save resources and time whenever we can. This is especially useful if we're working on a long-running project, and we can use our resources to crack hashes sometimes, but not all the time. We can dip back into our work for a little while, and then leave it aside. Of course, we can always pause a HashCat session through the interactive interface, but if we need to step away for a long period of time or perhaps reboot the system or something like that, using a session will preserve our place for us. If we don't provide a name for a session, HashCat starts a session called HashCat, and we can pause or quit and resume this session as well. But it will be replaced if we run a new HashCat cracking session without giving it a name. So it's usually a good idea to name any new session we start, especially if we expect it to take more than a few minutes, just in case. Another way we can manage our cracking job is to set the workload type. By default, HashCat runs at a moderate workload profile, where it doesn't dominate the activity of the system if there's other things going on. HashCat is, by its nature, quite resource-intensive, but at the normal workload level, other operations can still compete on nearly fair ground for resources. But we can crank up the workload profile to levels that we'd only really want to use if we're not doing anything else on the system that's running HashCat. We can set a workload profile with the W option and a number from 1 to 4 or low through nightmare. The default is 2. Higher workload modes can cause the system or the screen to lag pretty seriously. And as always, if you choose to push your hardware to its limits, be aware of the risks. We can also set other parameters for our cracking session, including the runtime, after which HashCat will stop. The temperature limit, which if it's reached, HashCat will back off. And the frequency with which HashCat shows status updates. We can always press the letter S to see the current status. But HashCat doesn't update the status view every time something changes. That would be something like thousands of updates a second. We can also output the status to SON instead. We can also tell HashCat to use an optimized kernel if it's available for our workload type. We'll use the O option to set this. And if an optimized kernel isn't available for the algorithm we're targeting, HashCat will tell us and continue on its way with a pure kernel. Optimized kernels are designed to be extra efficient at certain algorithms, but they have a limit on the length of passwords they recover, so there is a trade-off. Usually the password limit is pretty generous though. We can also pass along options for tuning the kernel in terms of acceleration and loops, but we won't be getting into that here. Spend some time with the HashCat help or man page to see all the options that are available. There's a lot of customization we can do should we need to. Distributing work across multiple devices. While we can work with one device on one system to crack our passwords, if we have more hardware available to us, we might consider using that to speed up the effort. HashCat defaults to using all available discrete JUPs and distributes the work they do automatically. So if our system has more than one discrete JU that has OpenCL support or other supporting software like CUDA, HashCat will just use them to perform its work and will handle dividing the work between them automatically. We can also instruct HashCat to use our system's CU in addition to the JU or JUPs by specifying that type of device, which is device type 1 when we run our command. We can use this by itself or in addition to device type 2, which is JUPs. CUS usually don't come anywhere near to the performance of even a moderately powerful discrete JU, but every little bit helps. There's also a device type 3, which is for FOGs and other accelerators that our system might have. So on one system, we could use up to 3 different types of device at the same time to perform HashCat calculations. Another approach for speeding up work by using more than one device is to distribute our work across multiple computers with a little bit of planning. There's a couple of ways we can approach this. We could use a command like split to chop our hashes file into chunks, and then we'd just run HashCat with our chosen attack mode and other details on a different chunk of hashes on each system. Or we can calculate the total key space for a given attack and divide that up to run certain portions on different systems. That way we'd have the same hash file on all our nodes, but each instance of HashCat would only stay within its allowed range of the key space, so it's not duplicating work done by other nodes. We'd get the total key space with the -- key space option, and then we'd use -s and -l to set the start and end or limit of that node. Then in either case, when the systems are all done, we'd collect our output files and stick them together with cat or some other tool, and then we'd have the hashes that were recovered from multiple systems. The HashCat binary can operate a service called Brain that can help us out when we're using multiple systems to crack hashes, especially slow hashes. The Brain service runs on a Brain server, which is just an instance of HashCat in Brain server mode, and clients connect to it whether they're local clients on the same system or other clients across the network. The Brain server keeps track of what hash attacks have been tried against a particular hash list, and it can tell clients to skip a certain range of attacks if it knows those have already been tried. So this saves time whether we have one client or more clients either running similar attacks or running attacks that would have overlapping strategies in some part of the key space against exactly the same hash list. When we use Brain, we can specify a session name, as with a regular individual session. This allows us to have separate Brain instances for separate sessions with separate hash files. The Brain files are stored in whatever directory the Brain server was started up in, so it can be useful to make sure you're working in a project directory or something like that when you start it up. On our server and on our client, we'll set a password, and we can also set a server address and a port if need be. And of course, across the network, we need to ensure that our firewall allows traffic to flow. HashCat runs on port 6863 TS by default, and if we're using a name session, we'd need to provide that when we start the client up as well. Here in my system, I'll start up Linux and then I'll start a Brain server. I'll do that with HashCat Brain server, and in this case I'll set a password. If I don't set a password, HashCat will generate one for me, but they can be pretty complex, and we'll keep things simple here. I'll create another window with Crethbase, and then I'll start up a Brain client. I'll use one of my other hash files here, the SHA-512 crypt one, which is mode 1800, and I'll use a basic mask attack so we can watch what's going on. I'll use an optimized kernel, and I'll set my output to 512 or 7 this TSDS. To tell this client to connect to my Brain server, I'll use --brain-client and --brain-password and provide the password that I set for the server. When we use Brain HashCat, we'll enable the use of slow hashes by default, and as HashCat clients try attacks, the progress is reported back to the Brain server, so other clients that connect later will be able to be told what to skip and future cracking attempts. I'll run this, and here I'll be able to see information being sent to my server as the client works its way through the key space for this attack. I'll switch over to the server window here, and I can see that information coming to the server session here. Brain server saves this information to the disk every few minutes, and it also saves it when the process is ended by pressing Ctrl+C. This information is stored in hidden files with file extensions ending in DMP, because the Brain server remembers what attacks have been tried. If we run an attack and then change it slightly and run it again, Brain can tell our client what portion of that attack was already tried, saving time and allowing the client to focus just on what's new. The Brain client offers 3 modes of reporting information: sharing attempted passwords with a server, sharing attacks that have been tried, which is the default, and sharing both. If you want your Brain server to keep track of attempted passwords, using mode 3 can be useful, but it can also be resource intensive both in terms of network traffic and disk space. A Brain server doesn't operate a central results file though, so you would still need to gather results from an out file on each client. Only the client that cracks a password will have that password in an easily usable form. You can read more about Brain server in the release notes for the version of HashCat where it was introduced. Out of the box, so to speak, we have a few different approaches for splitting up work on different systems. We can split our hash list and run attacks against portions of that on different systems, or we can use the same hash list on different systems and tell systems to only focus on a specific subset of the key space. We can also have the Brain service coordinate the attacks that each client tries, but this will only work for clients that all have the exact hash list. This is helpful even if we just have one client. Developing a strategy to take advantage of more than one system takes some planning and some work, but if you're not inclined to do the manual setup, intending that a distributed solution requires, take a look at tools like HashTopoly, which automates a lot of this work for us. Planning your cracking session. Now that we've seen some basics of how to use HashCat, we have a framework to start planning a cracking session. Having a plan is important, especially when we're embarking on a task that consumes resources that can be expensive and which can take a considerable amount of time to complete. So before we start a cracking session, we should gather some information and develop a strategy. First, we'll need to get our hashes in order. We might have only one hash, or we might have many. In either case, we should put the hash or hashes into a file. And if there are many types of hashes, we should make sure we have only one type of hash per file. We can use tools like HashCat to determine the hash type, and we'll use that information when we write our command. This information will also help us decide whether to use the slow hash mode or not. Some hashes are slow and others are fast, and HashCat can use more advanced approaches to slow hashes with this option. And of course, if HashCat doesn't support a particular algorithm, we should spend some time looking at other tools, like John the Ripper, instead. Second, we'll need to develop our strategy for how we'll attack our hashes. Will we use a dictionary attack? Do we have a word list that's suitable? Or will we use a word list and some rules, or a brute force mask informed by some information we know? It's extremely useful to have any available piece of information about the passwords our hashes represent. Some systems restrict the characters that can be used in passwords, and even worse, some restrict the length of passwords that users can choose. Information like this can help us choose a mask if we've decided not to use a dictionary attack. Or we may choose to take a layered approach. Perhaps we'll spend a short period of time running a dictionary attack, then a dictionary attack with rules, and then fall back to a mask attack with various strategies. Depending on the information we have available to us, it may be useful to explore other HashCat tools like the Keyboard Walk Processor, Prince Parser, Stutz Posters, or Mask Processor to see what they can add to our strategy. These tools can generate word lists and rules that are informed by various statistical and other approaches. In some cases, we can estimate how long a cracking session will take based on our attack approach and our hash list. We can estimate the size of the key space using this chi-space option combined with our attack plan, and then we can estimate the speed of our attack with the speed-only option. However, if our hashes have salts and HashCat cracks one of those salts, it will reuse that salt in future attacks against the same hashes. So the attack time may reduce by a large amount at that point. And of course, an estimate is an estimate of solving the whole key space, and it's generally unlikely that our key will be the last candidate that HashCat tries. So it's usually better to focus on defining an efficient strategy and making sure we're not retreading ground we've already covered, instead of simply trying to optimize for time. Regardless of our attack strategy or algorithm type, there are a few things we should always or at least usually do. If your cracking session is likely to take more than a few minutes, which it probably will on anything but trivial hashes, consider using a session to keep track of the progress and settings for a cracking attempt, should you need to stop it and come back later. It's also almost always a good idea to specify an out file to collect recovered passwords on their hashes, so you don't have to consult the pot file or rerun HashCat with a show option after passwords have been recovered. In many cases, especially when we're working with slow hashes, it's useful to use the brain service to coordinate and optimize attacks. This gives us the flexibility to try different attacks against the same hash list on one or more systems, while not duplicating effort. And we should spend time to decide whether our hardware on our system is sufficient for our task, or if we need to add more, or if we need to add other systems to our strategy and divide up our hash list or our key space to make the work go more quickly. It's important to be aware of how the shell you're using interacts with what you type. When we echo hashes to a file, or when we write a mask, for example, some shells like Z-shell will interpret some of the characters itself, so we'll need to wrap things in single quotes to tell the shell to treat those strings literally. For example, if we echo hashes with $signs in them to files, we'll need to be careful about quoting those strings properly as well, so the shell doesn't treat them as variables. For it makes sense, consider wrapping up complex HashCat commands in a script. We can use line continuation characters in a script to keep each item on its own line, making our commands more readable and easier to modify. This helps avoid typos, and it can also help to create documentation for your tasks in case you need to revisit the details later. And basically, whenever we're working in a shell session, whether remote or local, it's a good idea to use terminal multiplexers like Screen or Tumpzivas to protect our process from being terminated by accidentally closing a terminal window or by disruption of our connection. Generally speaking, we need to start with what we know, and we need to know what success will look like. In many auditing cases, the goal might be to check that passwords are simply not easily crackable, and we may not need to actually crack the passwords, or we may need to throw all our resources at solving just one hash. Frequently, we'll need to do some additional work before or after a HashCat session. We'll need to get the hashes into a format HashCat can use, and we'll need to take steps to apply the result of HashCat's cracking to our desired outcomes. If you're not familiar with working in the shell or with manipulating text, I recommend you take some time to develop skills with that. And it's always a good idea to keep a lab notebook of ideas, commands, and both successful and failed strategies as you go. Exploring practical challenges. We've been spending time working with method hashes, which are not something anyone should really be using to secure information anymore, but they've allowed us to explore the HashCat software without spending large amounts of time or resources to crack example hashes. I've provided a few other hash lists in the exercise files for this course, which use slower hashes. They're made from the same password strings that the method hashes used, so you're welcome to practice your skills with those files using the appropriate hash modes. Let's wrap up this course by spending a few minutes looking at some practical challenges that a security auditor might face when exploring the security of systems. These still have fairly easy passwords to crack, but they'll let us explore more realistic cracking scenarios. These challenges are available in the Challenges directory in the exercise files. This directory has a Challenges file where I describe each challenge, and there are files with hashes, which you can use as you develop your solutions. The contents of these files are in what we might think of as their natural state, as we'd find them in the wild, so we'll need to do some work to get these set up to use with HashCat. There's 4 items here. The first is from the shadow file of an older Linux system, which is where the user passwords are stored, so that's a user account password in there. Second, there's a file from a web server's authentication system with a username and a hash password. Third, there's a hash Linux bootloader password. And fourth, we'll come back to the def file that I showed you earlier in the course. We've seen how to extract the hash, but we'll do that again here for practice. Over the next few videos, we'll handle each of these practical cases. Each of these challenges has one password to recover, and we don't need to use distributed strategies or other long-term strategies in these cases. Though we will need to make some choices about what attack mode to use based on information that the challenges provide, and we'll need to decide where to start in terms of preparing our files, using word lists, applying rules, and employing various strategies that we've seen so far. If you'd like to try out recovering the passwords on your own before watching me do it, pause the course here. When you're done, or if you want to follow along with me instead, continue with the other sections to see how I approach each of these. Linux user account password. Our first practical challenge is to recover a hashed Linux user password from an older Linux system. Modern Linux has moved to more robust hashes for passwords, as we'll see shortly, but Linux lives forever, and there are quite a few older Linux systems out there that security auditors might come across. I'll move into my challenges directory, and let's take a look at the file for this challenge. This challenge provides a line of text copied and pasted out of an etc. shadow file where Linux stores hashed user passwords, so it has some extra information that HashCat doesn't need. I'll make a copy of this file to work on. I'll copy one shadow file to one hash, and then I'll open up one hash. In this case here, we don't need the username, so I'll remove that. And we don't need these fields here at the end representing the password expiration and things like that, so I'll remove those and then I'll save this file. Now let's see what hash mode we'll need to use. I'll run hashadum 1 hash. And I can see this is a Shamanus 512 crypt hash, and I'll use HashCat mode 1800. Okay, now we need to decide about our attack strategy. We weren't provided much information, so let's start out with a fairly simple straight or dictionary attack to see if this password is the same as one that's been leaked in the past. There are of course millions of leaked passwords, but a dictionary attack is pretty straightforward as long as we have a good set of word lists. Earlier I mentioned that we can get word lists from various sources online, and because we're going to be doing some password cracking in this chapter, and because it's a useful resource to have, I've spent a couple of minutes cloning the seclists repository that I mentioned that's in my home directory. There's a lot of lists in here, and we could try them all if we wanted to, but let's start fairly small and choose a subset of the lists to start with. I want to check if the password matches any leaked ones, so I found the leaks databases directory inside of the passwords directory in the seclists repo. Let's take a peek in there. This seems like a good place to start. Okay, let's pull all of this together and see what happens. I'll clear the screen and I'll write my HashCat command. I'll write HashCat M1800 and then provide the file that contains the cleaned up version of my hash. I'll use attack mode 0, and then I'll use all of the word lists in the leaks databases directory from the seclists repository. I'll use an optimized kernel. I'll enable slow hashes. And I'll set my output to one result cheese.ts. Let's give this a try. I can see the progress as HashCat uses each word list in turn. My job is finished and I see that the status is cracked. HashCat found a password. Fantastic. Let's see what it was. Alright, cat1 result cheese.ts. Here I have the hash was working on, and here's the recovered password. Oh no, well, we'll need to talk to this user about their password strategy, and maybe we should recommend that the system administrator set a longer minimum password length, or that they introduce a policy of requiring more complex passwords. While this password does follow some best practice advice in that it uses a symbol and it technically doesn't contain a dictionary word, it's pretty short, and sequential numbers and basic substitutions are commonly used in leaked passwords, so this is a pretty bad password overall. Good that we found it before someone less trustworthy did. This example uses a hash type that Linux distributions used to use, but modern distributions have moved on to another hash type called YesCrypt, which is designed to be much slower to crack. We can see that represented by the Y section of the hash. The previous type we looked at had a 6 there instead. At the time I'm recording this, HashCat doesn't support YesCrypt yet, but John the Ripper does. That's an example of how we might need to choose different tools to accomplish our goal. At the bottom of challenge 1, there's 2 descrypt hashes you can use to experiment with should you like to. You can break them using John and the format crypt option. This reminds us to keep in mind the fact that sometimes HashCat won't be an appropriate tool to do what we need to do, so sometimes a little bit of research is required in order to achieve our goals. Apache account password. Our second challenge is a line of text from an internal corporate Apache web server, where there are users and passwords set up using the software Tapshazoid. Let's take a look at that file. Alright, cat2 Tapshazoid, we don't need to do much to get the file ready for HashCat, because we can use the username option to just ignore this very clever and super hard to guess username, but to find out what the hash type is, we'll need to run HashCat. HashCat isn't going to like this format, so I'll just copy the actual hash here, and we'll pass it to HashCat directly. I'll write HashCat on, and I'll use single quotes here to treat this as a string literal. And I can see that this is hashtag mode 3200. If I left off the quotes or used double quotes, I'd get a garbage response because in this case, the shell would read terms starting with $sign as variable calls. Actually, let's take a look at that. Once again, I'll write HashCat in, and without any quotes I'll paste my string and I can see something interesting is going on here. Looking at my hash, I can see what's going on. These values in front of the slash are being interpreted as variables, and that turns the string into something that HashCat doesn't know what to do with. So it's always important to use quotes when we're working with these strings. If you want to learn more about how the shell operates, take a look at my courses, Learning Linux Command Line and Learning Bash Scripting here on our channel. Alright, we already have a file that's in a format we can use and we know our hash mode, so let's get cracking. We are told this file came from an internal corporate system, so let's try out some common corporate passwords, but let's transform those with a rule. So we'll need a word list. And earlier I mentioned we can get some of those from the seclists repository. I've already cloned that, and inside there I found a word list called Common Corporate Passwords, slc. So that sounds like a promising start, and we decided to use some rules as well. So with common corporate passwords, let's use the Topton 2023 rule that's part of the HashCat repository. Maybe this will work and maybe it won't. This attack might take a while, so let's make sure we're running our brain server in case we need to change strategy and save some time later. I'll start that up with HashCat's brain server, and I'll set a password. I'll create a new window here with Ctrl+BC, and I'll move into my challenges directory. Now let's write our HashCat command to start our first attack and connect to our brain server. I'll write hashcat m3200 and provide my file. I'll pass along the username option to tell hash to ignore the username at the front of this hash, and I'm using a dictionary attack again, so I'll use n0. Into that I'll provide my common corporate passwords list, which is in my user directory, seclists passwords and common corporate passwords slency. We're also applying a rule to this attack. To do that, I'll write R and provide the Topton 2023 rule, which is in my user directory, HashCat rules at Topton 2023. I'll use slow hashes, and I'll put my output in two results to use TS. I'll use Brain client and specify my Brain password. Let's see if this works. No results. We've exhausted this key space with no recovered new digests. Okay, that's fine. Let's try another rule. Maybe the best SCST6 rule that we saw before. They are the best after all. I'll clear my screen, and I'll recall my previous command and I'll edit it to use the best SCST6 rule. Let's give this a try. No luck there either. Okay, let's get a bit more aggressive and start using some of the bigger, longer rule files. Let's try the Rockio Mines in 30,000 rule. That file has 30 rules that are related to the Rocky word list, which is a list that contains a lot of real-world passwords. I'll clear my screen, and again I'll recall my previous command and I'll change to using this rule. Let's see if this works. I'll press S a few times to keep an eye on the status. There we go. Now we have a cracked result. I can see that we've recovered one new digest. That didn't take too long. I'll clear the screen, and let's take a look at our result. Here I can see that the password is SpringFentory25. That's not likely to have occurred just on the common password list yet at the time I'm recording this, but I'm sure it'll show up in the next big list of leaked passwords. However, a slightly older word list combined with a rule got us there anyway. Other combinations of word lists and rules are likely to get us to this result as well. When we try to recover a password with HashCat, we have to start somewhere, and we won't always get our strategy right on the first try. So we need to make that first guess, and then think about how we can improve our strategy as we go along. And Brain helps us out when we do this, because it helps us avoid repeating work that's already been done against a particular hash list. Linux bootloader password? Linux systems can be protected by a grub password, which is a password that grub, the Grand Unified Bootloader, asks for before allowing the system to boot. This is different than an encrypted disk password, which we'd have with a Lux volume. And so if we have a Linux system that isn't encrypted, but which we can't boot because we don't know the grub password, we'd likely still be able to access that system's disk and find its hashed boot password. This challenge asks us to imagine that we're auditing a group of servers at our company, and we need to ensure that we have a record of their boot passwords. Our system's boot passwords follow a prescribed pattern. The data center abbreviation, the last 4 digits of the system's primary MAC address, and then 2 random letters and 2 random numbers. We know the first 2 parts of this password. The system is in the Los Angeles data center, and we use LAX for that part. The system's MAC address ends with byte 3, so that's fine. We don't have the rest of the information, but we know what the range of possibilities is. The last 4 characters are made up of 2 random letters, uppercase or lowercase, and then 2 digits. So let's use HashCat to recover the password using what we know to help discover what we don't know. Because this password is something that our company has designed based partly on information that we know about each server, the password is not likely to be one that has been leaked from another source, and it's not likely to be a variation of commonly used passwords. So we need to start off with a brute force attack though. Luckily, we know most of the password already, and we have clear parameters for the part that we don't know. Brute forcing, even just an 11-character password with most kinds of slow hash, would take a very long time. So let's put together what we know, and use a mask to represent what we don't. We know the first part of this password based on information we already have, so that's just going to be explicit or literal characters. The next part is 2 random letters, and those could be uppercase or lowercase. We could use the token here, but that's a little bit inefficient, because it includes lowercase and uppercase letters and also symbols and digits. In this case, that inefficiency isn't too big of a deal, but we can use a custom character set to only try out lowercase and uppercase letters in this scenario. To do that, we'd add a custom character set, number 1 in this case, and say the characters there are all the lowercase ones and all the uppercase ones. Then, we'll use that 1 token for the first 2 characters. And the next 2 are digits because we know those are just random numbers, so we'll use the T token for those. Here's the file for this challenge, and we'll need to do some work to get it in a format that HashCat can use. So let's make a working copy. I'll write kp3grub40 custom to 3hash. Okay, I'll open up my copy, and I'll delete everything except the hash here. I'll save this and I'll close my editor. Now let's see what type of hash this is. I'll write HashCat3hash, and I can see that it's grub2, which is HashCat mode 7200. Alright, I'll clear the screen. And let's put together our HashCat command to see what happens. I'll write HashCat M7200 and provide my hash file. I'll write in 3 for a mask attack. And then I'll use -1 to define my first custom character set. In this case, the lowercase and uppercase characters. I'll provide the static part of my string, and then I'll use a 11dd as we saw before for those custom characters and then digits. This is a cadcuf hash, and that's one of the ones designed to be slow. So I'll use is for slow hashes. And I'll put my output in 3 results TSDS. And let's go. My status is cracked, and I can see that HashCat has recovered a new hash. So let's take a look at that. I'll clear the screen. And then I write cat3 result TSDS. Here's my recovered password. And I can see those last 4 characters are TDing too. We should make sure to write that down in the notes for this server, in case another administrator or auditor needs that information. While we can use HashCat to brute force an unknown password, that generally takes a very long time for anything other than trivial, fast hashes like miftiv. So if we need to brute force a result, we should try to be as precise as we can be with the information that we know. That's not always possible, but when they are appropriate, mask attacks are a really helpful tool. Password protected def file. Def files can be password protected. When they are, they require a user to enter a password before the user can see the file's contents. In this challenge, we're asked to help recover the password from a def file. HashCat only works on hashes, not directly on files, so we need to extract the hash from the file in order to give the hash to HashCat to crack. In this case, we'll need to use a tool to extract the hash. There are many tools that can do this, but the one that comes with John the Ripper works well. The file we'll be working with is here in the challenges directory. To extract the hash, I'll run fdut1 play. To do that, I'll put in the path to my home directory, the location where I cloned the John the Ripper repository, run fdut1 play in this case, and then I'll provide the name of my def file. This will output the hash to the screen. But let's put it in a file for safekeeping. I'll redirect the output of this to 4hash. We'll need to clean that file up a little bit, so I'll open it up with my text editor, with nano4hash. And in this case, we'll just get rid of the file name here at the beginning. Now let's use HashCat to see what mode represents this hash. I'll write HashCat4hash, and up here I can see that it's mode 10,500. It sounds like our coworker is pretty certain that the word spring is involved in the password, but maybe it's capitalized at the beginning. And it seems like the number after that could be of an unknown length. It certainly doesn't seem like we need to use a larger word list or rule set to transform a word list for this attack. The parameters are pretty narrow and we know a lot already. So let's use a mask attack for this challenge, and let's once again use a custom character set for the uppercase and lowercase s to reduce the key space. Then we'll use the rest of the word that we know, and then we'll look for it maybe 6 digits to see if there's a typo at the end. We'll use increment to try out increasing lengths of digits within our 6-digit mask. So that should pick up 25 and 2025, and so on. If we don't find anything with that mask, we could always switch those to the a token for any character later on. So let's write our HashCat command. I'll write HashCat M10500 for this def mode, 4hash, which is the hash that we've extracted from the def file, and we'll use attack mode 3 because we're using a mask. My custom character set, the first one, will be capital S and lowercase s. We are told that this password started with the word spring and spring starts with a letter S. So we can reduce our key space by only using characters we expect to appear in a certain position. We'll use this custom character set for the first letter, then we know the rest of the word pring, and then we'll provide space for 6 digits with a d. We'll use I for increment, and S for slow hashes, and we'll put the output in for result tsds. I run this. And here I can see that this password has been cracked. It looks like HashCat found the password using 5 digits. Interesting. Well, let's take a look and see what that password was. I'll clear the screen and then I'll write cat for result tsds. There's our hash and here's our password. Haha, it looks like instead of typing 2025, our coworker typed 20,205. Happens to the best of us. Let's open up that newsletter, just to check that the recovered password worked. I'll type in capital S, lowercase pring 20,205. Seems like it worked. Great. We've solved this challenge. Even though we were given a file, we can use various tools to transform this request into a fairly straightforward HashCat attack. This reminds us that HashCat is one tool among many that we might need to use in order to complete our task. Next steps. We've spent some time exploring hash types and attack modes, and we've seen how to manage our password recovery sessions using HashCat. Whether you're spending time to learn about how hashes work as part of a computer science program, or as part of a software development or cybersecurity career, or you're an auditor checking systems for compliance, HashCat is a powerful tool for password recovery. We've been using really fast hashes for the most part in this course, so we can learn how to use the HashCat software and learn how to develop an attack strategy, but most hashes that we'll come across in real life are much slower, and they'll take a non-trivial amount of time to attack. I've kept things quick in this course, because the only thing more boring than watching someone type out long commands is watching someone else's computer do work in real time. So I encourage you to spend some time with the slower hashes that I've provided, and to generate or find some of your own, to get a better sense of how your hardware will perform when cracking slower hashes. It's important to remember that HashCat is one tool in a collection of tools. Often it's the star of the show, but sometimes it's just a component of our overall task, and sometimes it's not the appropriate tool for the job, and we'll need to reach for something else instead. It's also important to remember that because of what it does, HashCat can be used to violate trust. Trust is everything, and it can be lost in an instant. So it's up to us to use our skills and tools safely, ethically, and responsibly. See you next time.